Welcome to another Mathcast. In this episode, we're going to be taking a look at another separation of variables problem, except this time it's a little bit different. As you notice, looking at the differential equation that we have here, this part of the differential equation is in standard form, as you remember from the last video. But then I also have another condition. This is called the initial condition. And if you remember in the last video, we ended up with an infinite family of solutions called a one-parameter family. And the idea is by appending to the differential equation this extra condition, this condition allows me to uniquely pick out one member of that family. Together, these two things, the differential equation and the initial condition, form what's called an IVP, or an initial value problem. Initial value problems are at the heart of just about everything we're going to do this semester. Now, what you're going to notice as we walk through this problem, the steps are going to be almost identical to what we did on the previous example using separation of variables. We're just going to have one final step to pick out the correct answer. And so we'll go ahead and start the way that we have become accustomed to, and that is by trying to separate variables here. This one's a little bit more complicated, but I'm going to try to get algebraically everything involving y on one side and everything involving x on the other. So my first step here is going to be to add y over to the right hand side. After doing that, I can see that if I pull out the y, I should be in good shape here. And then I can separate variables. Divide the x and multiply through by the dx. Okay, it's at this point that I have the variables separated, and so as we recall from last time, I'm going to integrate over the top of these. Let's make the integral on the right-hand side look a little bit better here by separating out the x on the numerator and the denominator. And then I should be able to integrate this. So if we look, the integral of dy over y, that should be the natural log of the absolute value of y. And on this side, you have one x that cancels here. And so you're looking at the integral of 2x, which is just x squared. And then the integral of 1 over x, which is the natural log of the absolute value of x. And then remember, both sides produce a constant of integration, but we're going to lump it together as one constant here plus c. And I can't stress enough how important that arbitrary constant of integration is, because without it, we wouldn't be able to apply the initial condition like we're going to do here in a little bit. All right, let's exponentiate both sides. So this is very similar to what we did in the previous problem. We will drop the absolute value, which is going to make this plus or minus, and then this will be e to the c times e to the natural log absolute value of x times e to the x squared. All right. Just as we did in the last example, I'm going to rename e to the c. I'm going to rename that a. It's just an arbitrary constant. E to the natural log of the absolute value of x is going to produce an absolute value of x. However, I already have a plus or minus in the problem, so introducing another absolute value isn't going to do anything here. So I'm just going to call that x, and then we have e to the x squared. And so, as you remember from last time, this is our general solution. And then if I wanted to apply the initial condition, I need to figure out, okay, y at 1, that is a times 1 times e to the 1 squared, which is just a times e, which means that if I want to solve this and set it equal to the initial condition, I need to set it equal to 1. Right? So y of 1 equal to 1, which implies that solving for a, which is the parameter, you always want to solve for the parameter. So solving for a, we have ae equals 1, or a equals 1 over e. All right, if we update our solution with that value, then our solution is now y equals plus or minus 1 over e, x e to the x squared. And this is now called a particular solution, except I've got one more thing I've got to resolve. I said before that the initial condition allows us to pick out one solution. And so the question is, which of these one solutions works? Well, if I want the value at 1 to be 1, then I need to pick out the positive value. So this negative is not going to work. So only the positive value will work to satisfy the initial condition. So my final solution here is the positive branch of the solution. And that's because of the initial condition. And so one of the things you'll see this semester is anytime we have an initial value problem, we're going to get a unique solution. In fact, later on in this chapter, we'll talk about the conditions for which we know a given differential equation will have a unique solution or not. All right, I hope you got a lot out of this episode. Thank you for watching.